Hi friends!
Now in our series to date, we started with a shellcode loader, we added a remotely hosted payload, and then we learned how to think about and address a number of poor OPSEC choices to improve the overall quality of our payload. Now, on a pattern level, we can also observe that in our 3 episodes thus far, the improvements have all been linear. We started with something simple, we then improved on that, then once again in our 3rd lesson we just built on that. And so this might give the impression that there is this one ultimate path to create the righteous hack lead payload. That one just starts simple and progressively layers in a linear fashion a variety of improvements, and then after a certain iteration you now enter the domain of the lead. But of course this is not the case. As I've mentioned before, when designing malware in general there are numerous branched design decisions and there's rarely a right and wrong path. Different decisions you may take each have their own pros and cons, and it's up to you as the designer to weigh these against each other and decide what shape your payload should ultimately take. And so as a simple example, I mentioned before that if we decide to change from a hard-coded payload to a remotely hosted payload, we might decrease the risk associated with static analysis, but at the same time potentially increase the risk associated with dynamic analysis. And so, guided by your own skill, preferences and goals, as well as knowledge about the target environment, you have to ultimately figure out how to best configure the payload for your specific use case. So I'm placing a lot of emphasis on this now, not only because it's a very important high-level principle, but from today's lesson onward, we'll explore different options on doing things. So there won't be a single branch moving forward anymore. I'll often present multiple options on how we could achieve something, and it would be your decision on what path to choose. Great, and so in today's lesson, we'll take our shellcode loader as we have it to date, and then we'll actually roll back the fact that we're remotely hosting our shellcode, and we'll once again hard code it. Now this might seem like a regression, but in line with what I just said, we'll actually apply another technique in our attempt to avoid static analysis, encryption. Now to be clear, we could actually keep our payload remotely hosted and use encryption at the same time. They're not mutually exclusive. And perhaps, if the added flexibility that remote hosting offers was of paramount importance to us, we would indeed do so. But for today, I just wanted to reduce some complexity so we can shine a brighter light on what we want to focus on in this specific lesson. And in that very same vein, I've also removed the sleep timer and junk code dummy functions that we added in the previous lesson for the exact same reason. But keep in mind, now we do have these tools in our toolbox. And in the end, we'll do a grand culminating project putting everything we've learned together, and then we'll be putting those skills back to use again. And so in today's lesson, we'll do a very brief and decidedly non-technical overview of encryption. I've done my best to stick to common parlance as far as possible because I just want you to get a sense of what encryption is and why we use it, rather than being able to understand its technical intricacies. We'll then review 2 applications. First, we'll look at a brand new separate application that we'll use to encrypt our shellcode. And then we'll look at our shellcode loader and see how to implement the ability for it to then decrypt the shellcode before performing the core actions we are now well acquainted with. I'll then run a quick demo just to show how the whole process works. And then today I'll also introduce something new. We'll integrate a few breakpoints into our loader. And then once the process is running, we're going to attach x64dbg to it. This is going to allow us to peek into the memory of the process so we can get a better first-hand glimpse of exactly what's going on. And one final thing before we get going, I have of course once again included the source code right at the top of the description. I encourage you to download it, open it in your favorite text editor or IDE, and then as we cover specific sections, you can always use it as a roadmap to refer back to in order to help you understand how it fits into the bigger picture. But you'll notice that today there are 3 separate links. The first is the application that will perform the encryption. The second is our loader that now also includes a decryption function. And then the third link is essentially the same application as the second link, that is our loader, but I've also added some hard-coded breakpoints, and we also print some debug info to the command console. And I've done so just so that we don't need to manually set breakpoints when we run x64dbg. Okay, and so with all of that, let's get to it. And so, as already mentioned, this is not going to be an exhaustive, overly technical breakdown of encryption. If you would like to understand the technicalities better, specifically how it relates to AES encryption, then refer to the link I've included at the top of the description to an excellent lesson on the computerphile channel. Now, as I've mentioned many times before in this course, MSA Venom is an incredibly popular tool for generating shellcode, and as a consequence, any shellcode it generates will be in a signature database. And so, for example, here, when I run this command, we can see the output right here. And so what I mean is literally these specific bytes in this order is in a database. And so if a file is written to disk and scanned and it contains these bytes, well, then that file will immediately be removed or quarantined. And so then the question for us becomes, is there a way to change these bytes in a way where the ultimate functionality is unaffected, yet where they are then different and unique enough so that they are no longer in a signature database? And the answer, of course, is yes, there is. And indeed, in this context, that is the entire point of encryption. And so we take our pre-encrypted shellcode, generically known as plaintext, and we apply to it a mathematical formula known as a cipher to get what can essentially be thought of as disguised shellcode, aka the ciphertext. But there's one very important piece missing here. Obviously, if we just took shellcode and applied a known formula, well, then creators of defensive software could also just do that and then also have the encrypted version in their signature database. And so that's why we then also use a unique key, which you can just think of as a password really, which ensures that the end product, that is our ciphertext, is unique and not in a signature database. And so the ciphertext is a product of both the cipher and the key. Meaning, if we have the exact same plaintext and we use the exact same formula, but we use two different keys, well then we would get two different ciphertexts. And so it is the key that ensures the end product is unique. Note, this isn't really the whole story. There is also something called an initialization vector, which can contribute to the uniqueness of ciphertext, and we'll cover that when we review the actual code. But for now, as a big picture, this is a good way to think about it. And so this is also in a very simplified manner what distinguishes encryption from encoding. When encoding, there is no key. And so if we apply the same encoding schema, let's say base 64, to the exact same source code, then the result will always be the exact same. And this is why encoding is not used for obfuscation purposes, but rather for other purposes, for example, the graceful transfer of data across networks. And so to quickly just once again summarize why it is we're using encryption, first off, we have to remember that our application, that is our code, will exist in two different realms. First, it will be written to disk, where there is signature detection, and then once it runs, it is loaded into memory, where there is no signature detection. And so here our application, i.e. our loader, contains encrypted shellcode when it is written to disk, and so it will undergo a signature scan. But since the shellcode is encrypted and unique, it does not reside in a database, and so no match will be made. Then when our application runs, it's loaded into memory, and now here in memory it's decrypted into its original form and executed. Now here the encrypted shellcode is of course the same as the one that is in the database, but as I just mentioned, signature detection will not take place in the memory per default. So just a quick point of clarification. It's not that signature detection is incapable of running in memory. It can run in memory, and indeed if something is, for example, suspected of being malicious by an EDR, an in-memory scan will be performed. But scanning in memory has a huge performance cost associated with it. And so whereas it's relatively trivial to scan everything that's written to disk, when it comes to the memory, the application of signature detection has to be much more selective. Now finally, before we move on, I do want to mention that there are different encryption standards, and today we'll use what's known as AES, or the Advanced Encryption Standard. Now really all that matters here is that you know that this is a very common encryption standard, meaning there is a wide availability of good libraries we can use in almost any language, and if used correctly, it's also an incredibly secure standard. And so indeed, out in the wild, you'll see AES being used the vast majority of times. Okay, and so for today's discussion, i.e. a basic introduction to encryption, that about does it, so let's move on to our code. And so to reiterate, when it comes to encryption, there are two pieces to this puzzle. First, on our own system, we'll run a specific encryption application that will take the shellcode and encrypt it. And then following this, we'll take the encrypted shellcode and place it inside of our loader, as well as integrate a decryption function inside of it. And so let's first cover our new application that will encrypt our shellcode prior to embedding it in our loader. And so to produce encrypted shellcode, we essentially require three things. First, we require, of course, our pre-encrypted shellcode, which we'll generate using MSA Venom. And then we'll need a password, which in this case we'll provide as a command line argument. Note that in the theoretical section I mentioned the use of a key, but as you'll soon see when the application executes, it will basically convert our password into a key using the SHA-256 hashing algorithm. And then the third essential component is a salt, which is randomly generated each time the application runs. Note that the salt is not strictly required. We could generate an encrypted payload without it. However, it's good practice that ensures in a scenario such as here, where we derive our key from a password, that even in the case where we use the same password, a different key will result. And while we're on this topic, I do want to point out that, as I mentioned before, in the encryption function, we'll also use what's known as an IV or an initialization vector, which does something similar but different to the salt. So whereas the salt ensures we derive a unique key each time we use the same password, the initialization vector ensures that even if the key and plaintext were the same, different ciphertext will always result. Okay, great. So with that out of the way, let's quickly step through some of the high-level events of our code. So as I mentioned, when we launch our executable, we will provide as a command line argument the password we wish to use. The program will then immediately check if we did indeed provide it. If no, it exits with a message indicating this. If yes, we assign this password to a byte array called password. We then assign this shellcode we produced using MSA Venom to the payload bytes array, and I'll obviously run through this in the demo, but these bytes were copied and pasted from the terminal output after running the MSA Venom command. And below this, we turn our password into a key using the SHA-256 hashing algorithm. Now this is beneficial for a few reasons, but one of them being simply that the AES protocol requires our key to be either 128, 192 or 256 bits, with the last mentioned being the most secure. So using SHA-256 is also just a very convenient way to ensure that no matter how long the initial password is we use, the key will always be exactly the right length. Then here we create our salt byte array by calling on our generate random salt function. Just very briefly, we can see the code for that function here. We pass to it as the sole argument the size of our desired salt array, in this case 16, and it will randomly generate those amount of bytes and then return it in the end. And then now here back in our main function, we get to the marrow of this application, generating our encrypted payload by calling on our encrypt data function and passing to it the three essential components: the unencrypted shellcode, the key, and the salt. So let's take a quick look at this function. Again, I don't want to dive into an overly technical exploration of encryption, so I'm gonna black box a lot of the details since we don't really need to know exactly how it works in order to use it. So you can see here we are using the Rijndael managed symmetric encryption algorithm. Now, just so you are aware, while AES is the encryption protocol or standard we're using, the actual cipher, aka mathematical formula, used by AES is called Rijndael. So I just wanted to point that out in case you were wondering what this weird freaky deaky Dutch term was. Here are two lines where we just define the size of the key and block according to what is required by the AES standard. And then these next few lines basically ensure cryptographic integrity as well as selecting the appropriate encryption mode. And then finally here we get to this using statement, which will create a crypto stream object where the actual encryption takes place. It takes our input data, encrypts it, and then the output is written directly to the memory stream. And then here finally we extract from the memory stream a byte array using the toArray method and then return that. And then once this is done, we're back in our main function and we have all these lines, and they may look complicated, but all it simply does is print our encrypted payload, salt, and password values to the console so that we can conveniently just copy and paste it directly into our actual payload loader. Okay, so that's it for the encryption application. Let's have a look at our actual payload. Now, a lot of this is of course already familiar to you since we've covered it in previous episodes. Now, that being the case, I'm just going to cover the new code unique to this lesson. So if you feel lost or simply need a refresher, of course, feel free to refer back to the older videos on this same playlist. So here at the top, you can see all our using namespace imports for our managed code. We've now added a few new ones for today's code, namely system.io, text, and security cryptography. Below it is where we use pinvoke signatures to import unmanaged code, but this is unchanged from before. And then stepping into our main function, I've rearranged things a bit. Now at the top are the same constants we declared before, as well as here are the two lines used to hide the console window. And then here is our new code, and we can see here are the 3 byte arrays we declare containing our encrypted shellcode, our salt, and our password. Now once again, this entire section, all 3 of these lines were just copied and pasted directly from the terminal output of our encrypted application. Below this, we once again convert our password to a key by using the SHA-256 hashing algorithm. And then here we actually allocate our memory buffer using virtual alloc before we decrypt our shellcode. Note that we could reverse this order. It really does not make any functional difference. The only reason I decided to do it in this order is that it makes things a little bit more interesting when we peek at the memory using x64dbg in the last section of today's lesson. And so then here is where we declare a new byte array and assign to it the return value of the decrypt function. And so let's go and have a look at that. And so in very simple terms, I want you to really think of decryption as doing the exact same thing as encryption, but in reverse. Meaning here we use the same basic elements and we just change the order. And as a consequence, most of this code will be familiar to you. And indeed, we can see here the code is essentially the same as our encrypt function, except here below, when we have our using statement and our crypto stream object, we use it to decrypt and not encrypt. And we once again write the output to the memory stream, convert it into a byte array using the toArray method before returning it. And then here back in our main function, we now have our decrypted payload as well as our memory buffer, so the rest is exactly as it was before. We copy our decrypted shellcode into memory, we change our memory protection constants so that we can execute our shellcode, and then we go ahead and execute it. Great, and so that's it for the code. Now let's go ahead and do a quick demo. And so the first thing we want to do is generate some shellcode using MSA Venom. Now today's shellcode is actually a bit different, since instead of calling back to a meterpreter handler, we're just going to launch calculator on the target system. Now you might think, what's the point of that? Why would we want to launch calc.exe as an attacker? And the answer is, well, we don't. It's literally pointless, but it's a common practice serving as a proof of concept. Meaning if we can show that we can launch calculator, it means our shellcode and payload works, and thus in principle we should be able to get a connection to a handler. So why are we doing this? Well, when you spend a lot of time testing and developing and trying different things out, it can become quite cumbersome and a waste of time to constantly ensure you have a handler ready on a different VM and manage the connections, etc. And so I just wanted to introduce this to you today as a shortcut tool you can use when you're doing maldev by yourself. But of course, if you feel called to do the quote-unquote real thing and establish an actual connection to a handler, by all means go ahead and do this, since it obviously will also work. And so once we've run our command, I'm just going to go ahead and copy these bytes here. Just please take note that I'm not copying everything, rather only the curly braces and everything in between. And so now let's open our encoding application. And of course, just keep in mind that this part will also still occur on our own machine in a real world scenario. And so we can paste our shellcode right here and save the file. And now let's go ahead and compile the application and then run it. And so you can see here, I forgot to add a password. So let's just run it again and remember to add a password this time. And you can see it outputs to terminal our shellcode, salt, and key. And I formatted things in such a way that all we need to do here is literally copy all of this right here. And then here we open our loader script, and then right here we just paste it. So we can now go ahead and save our loader, compile it, and then we can run it. And even though it's minimized, we can see right here indeed that we have successfully launched calc.exe. Great, and so we have one more chapter in today's lesson, which is looking at the process private virtual memory space using x64-dbg while we run it. And so, well, why do we even want to do this? Well, I think it's honestly freaking awesome, but more than that, I did find in my own personal learning journey that whenever I experience things directly, i.e. in a concrete manner, it just really helps to solidify a lot of ideas that were mostly abstract up to that point. And so you've seen the code we've written, and now you'll see in the memory what that code is actually doing. And so I want to encourage you, when you are developing your own malware and testing it, always think about using x64-dbg or WinDBG, which is also excellent, or Process Hacker or PEBear, and use these tools to become intimate with the malware you're creating on different levels, because I really think it's going to help you to understand it better, and as a consequence you'll become better at creating malware. And so for this, as I mentioned, we're going to run an alternative version of our loader, which I've also linked in the description. It's the exact same code, but I've just added a few things, and I want to quickly show you what I've done. So here, right after we've allocated our buffer, we're going to print to the screen the memory locations of our encrypted shellcode, as well as this newly allocated buffer. And then using console.readline, we are essentially hard coding a breakpoint. Then here, after we've decrypted our shellcode, we'll once again share the location of our decrypted payload in memory with a breakpoint. And then we have another breakpoint after we've injected our decrypted shellcode into our buffer. And then here finally we have our last breakpoint right after we've changed our memory protection constants. So again, I've introduced these hard-coded breakpoints just to make things convenient so that we don't have to worry about setting breakpoints every single time we open the debugger. But I do want to encourage you that when you play around yourself, don't always do this. It can become a crux, and it's very important for you to also just play around with the debugger and become very comfortable with setting breakpoints there too. And so the first thing we obviously need to do is also compile this version of the code. Please also note here the inclusion of the unsafe flag. And so then once that's done, we can run it, and we can immediately see we hit our first breakpoint, and on screen is the address of where our payload is stored, as well as where our buffer has been allocated. Now, just as a quick reminder so that we know what we're looking at, the first 3 bytes of our unencrypted payload is FC4883, and the first 3 bytes of our encrypted payload is E727B8. So now let's go ahead and launch x64-dbg with admin rights. And once it's open, we can hit Alt and A, and we can attach to our debug loader process. And so we can go back and copy this first address. We can paste it and go there. And so we're expecting to see our encrypted payload here. And indeed, you can see right there is E727B8. And so now in another dump tab, we can copy and paste the address of our memory buffer. And we can see indeed here that it's still completely empty. And this is of course to be expected because we've not yet run marshal.copy. And so we can hit enter again to go to our next breakpoint, and we can see this address where the decrypted payload is stored. So back in x64-dbg, let's now select the third dump tab. I'm going to hit Ctrl G again, and I'm going to paste this address. And we can see right there, starting with FC48 and 83 is indeed our decrypted payload. So let's hit enter again. And now let's check back on the buffer that was just empty, and we can see now that the decrypted payload has been copied into it, FC4883. And now here on the top, let's head over to the memory map tab. We'll once again hit Ctrl G, and we'll paste in the address of our buffer. And we can see the buffer right there, and we can see that it is the read-write protection constant. And we can also see that initially it had the read-write protection constant. So now off screen, I'll hit enter once again in the terminal just so we can observe, and we can see right there our protection constant changed, while the initial is still read-write because obviously that won't ever change. And then finally, if I hit enter one more time, we can see that calc.exe launches. And so there's much more we can do here and explore further, but I'll leave that up to you. I just wanted to show you how we can peek inside of the memory and see reflected the very things we've been doing with our code. Pretty sick, bruh. Great, I hope you enjoyed that lesson. I left encryption to relatively late in this course. In most courses, you'll usually see it quite early on. But from now on, we'll pretty much always incorporate it in whatever malware we're writing. And so if you do other courses or tutorials, you'll see that having encryption in a payload is pretty much par for the course. So I've rearranged some things in my life, and I'm going to ensure a quicker turnaround on these videos now. So hopefully I'll get the next one out in circa 2 weeks. It will be on process injection and thread hijacking. Now, if you want to be sure not to miss it, please consider subscribing and hitting that sneaky notification bell. And if not, well, no worries, bruh. Until next time.
Peace out.